Yeah, Kumar. Thank you very much. It's been a few years since I came here. I guess COVID has interrupted many things in our lives, so it's a pleasure to be back. Okay, so I'm going to talk about adaptive. What? Which button is the point? The point is the first one. This is the pointer?
No, this is this one.
This one. Oh, okay. All right. Okay, sounds good. So yeah, so I'm going to talk about adaptive beam management in mobile millimeter wave devices, and this is completely the work of my ex-student Santosh Ganji, who just graduated with his PhD this year and is doing his postdoc with me. So you know the carriers in the US, I believe, have invested a lot of money in 5G spectrum, but they've not been able to use the millimeter wave uh, investment yet. So there's a lot of pressure, but somehow they're not doing it. So what I'm going to talk about is to show that millimeter wave deployment can actually be feasible relatively simply. Okay, and this whole talk will not have a single equation. All right. So in 2016, the FCC in the US came out with releasing 10.85 gigahertz of spectrum in the millimeter wave band, and 3.85 of that was licensed, and 7 gigahertz was unlicensed. And the way I like to think about this unlicensed, the release of this unlicensed, is the FCC, I think, learned from what happened with the 2.4 gigahertz band. So the 2.4 gigahertz band was the junk band used by microwave ovens, and nobody wanted to use that for communication. So they released it for experimental use by universities and so on. And a revolution started. All Wi-Fi started in 2.4 in this junk band. So they realized that giving unlicensed band, allowing people to experiment, actually is much better than trying to control it to the last decimal place. Okay. So 7 gigahertz, I think of as a confidence in innovation of academic and other research communities. And they in fact proposed to release another 18 gigahertz later. Okay. So now the millimeter wave band has a very high path loss. So it's 84 decibels at 28 gigahertz at 10 meters. And the way you overcome that is then by narrowing the beams. Okay, so packing your power into a narrow beam, and use an antenna array to do that. But the problem is that once the beam becomes narrow, then as the users move, the beams have to be switched. You have to keep pointing at the user. How do you do that? And that's the problem that they've not been able to solve. Okay, the issue is that there are two beams, the transmit beam and the receive beam. Let us say the mobile user and then the base station. And both these beams have to be pointed at each other. Okay. And how do you do that? Maintain beam alignment under mobility when the user is moving around. Okay? That's a big challenge. And it's and losing contact is very bad, because then you can have a up to 1 second interruption, because you have to reacquire the mobile as a new user, and that can take up to 1.28 seconds. Okay, like 64 beams you search, each about 20 milliseconds, so it can take up to 1 second. And then, of course, it interrupts all the high performance applications, etc. Another problem with the millimeter wave band is occlusion. So if you have a hand that covers the mobile and it comes between your mobile and the base station, then you have a temporary occlusion, a loss of 10 dB. Okay, and that 10 dB loss can cause the big damage is that you lose time synchronization. And this whole service is time scheduled. I schedule the opportunities to transmit to each other. Okay, And once time synchronization is lost, then again you have to acquire as a new user, etc. And blockages, unfortunately, give you no warning. I can just turn around while I'm talking, and that's a blockage, okay? Or somebody can come in front of me. So how do you recover from transient blockages without losing connectivity? That's the challenge. Okay, I'm going to show you two protocols. One is called BeamSurfer, and this does beam management during mobility and also for transient blockages. And then I'm going to show you another protocol called Terra, which gives you blockage resilience in outdoor millimeter wave networks. Okay, so let's first talk about what are the solutions that people have proposed in the past. And the solutions are unrealistic. Okay, so people have suggested determining the angle of arrival and departure of the beam and adjusting geometries and so on and so forth. But that's a very complicated thing. And in order to get angle of arrival, basically from individual elements of the antenna array, you have to get enough information. And that requires a high signal to noise ratio. And it's not necessarily going to work well, okay, in this case. Other solutions that people have suggested is motion prediction. They suggest additional sensors, accelerometers, gyroscopes, GPS, light sensors, etc., to determine orientation pose of your mobile. But this also is unrealistic because it requires very tight coordination across different technologies. Okay, so ideally, and control side channels also people have talked about having an omnidirectional channel for the control channel. But the omnidirectional channel's range is different from the directional channel's range. So it's not going to be able to assist necessarily when the directional communication is going on. Okay, so it is desirable. So we'd like to avoid knowledge of side information, and we'd like to do this complete alignment and tracking completely with in-band information, nothing extra needed, just say on the basis of received signal strength. Okay? And so my intuition is the following. Supposing you have a complicated control system, okay, and you want to point your beam in a certain direction. You don't need to model the whole world to do that. You just say if the beam, if something goes up, then you move up or down. So basically, you just go in the opposite direction. That's about it, right? You don't need to model the movement of the Earth and you're walking and so on. So control systems, when they're operating, they can operate in a very linearized regime with minute changes. So we should be able to do pointing that way. And that's what I'll show you. Okay, so that's called beam surfing. Now, the first thing to note is that the antenna gain. So can you see a red beam over there? So that's a red central beam. And what I'm showing here is the 3 dB bandwidth. So this from here to here is a 3 dB loss. And this is the 3 dB beam width. And after 3 dB, the loss is very dramatic. Okay, so you want to use this beam only for 3 dB. So the idea that we want to do is when we go down to 3 dB, then we will switch to the next beam and then the next beam and so on. So we want to surf the tips of the beams, okay? And experiments show that purely in-band beam management is possible by timely switching when the received signal strength drops by T dB and to one of the two adjacent beams. If it's a two-dimensional thing, it's one of two adjacent beams. If it's a three-dimensional, it's one of 6 adjacent beams, okay? All right. And now let us suppose the base station is transmitting to the mobile, then the received beam can be switched by the mobile, right? But to do transmit beam adaptation, you need feedback from the mobile to the base station. So the mobile adapts as much as it can, and when it cannot adapt anymore, it tells the transmit beam to change. Okay? It's a very simple system. Okay, so what is beam surfing? So these are the beams available to the transmitter. These are the beams available to the receiver. And consider a user going this way. So when the user is over here, he or she is using this beam. When they go to this side, they're using this beam. So they're basically going from this blue beam to this purple beam. That is from here to here. And similarly, the transmitter here, initially it's using this beam, then it is using this beam. So what does beam surfing do is very simple. On the mobile side, it's just going this way. On the transmit side, it's doing that. That's why we call it beam surfing. Okay. All right. So as a user moves, sure I need this video. So that's, again, this notion of surfing. And there is a state transition diagram, right? To keep track of things, when to do receive beam adaptation, when to do transmit beam adaptation, etc. Okay, let me show you a, okay. So here, so this is, there is a, this mobile is moving translational motion. And as it moves, this is the beam surfing that's going on. Okay, so it is switching beams at this point. Switching a beam at this point, then again this point, etc., etc. And for rotational motion, here's video. So we're rotating this thing over here, and this is the way it adapts. Okay. All right. And now what about transient blockage? Okay. So let us suppose that this base station is transmitting to this mobile over here, and this is the yellow beam here. Now let's suppose that that gets blocked by somebody. Okay. So as it gets blocked by somebody, then what you want to do is, it turns out, and we've done experiments, there is a reflected beam always in indoor environments. So you want to switch to the indoor, to this reflected beam, but not to carry your data. You want to switch to the reflected beam to maintain your time synchronization, so that as soon as the transient occlusion disappears, then you switch back to the line of sight beam. Okay? So it's not good enough to transmit data, but it's good enough to do the control channel information. So what is the impact? What is the impact of transient blockages? So you suddenly lose control plane information. That affects your timing synchronization. And remember that you have agreed with the base station to talk to each other at certain times, which means that both of you are pointing at each other. So if you miss that appointment, then you're lost, and you're kind of searching in space, and you cannot find that person easily in space because they have to be looking at you when you're looking at them. Okay. All right. And mobile loses connectivity, and reconnection is time consuming and also energy intensive. Okay. And these blockages are unpredictable. So any mitigative method must be proactive, because you have to be ready. Okay. And so this is, so experiments show, and we've done in our university building, experiments show that reflected paths are available in indoor environments. And so what we do is, when everything is working normally, we scan and keep one reflected beam in our back pocket. Okay. So we have one reflected beam. If anything goes wrong, I'll use the reflected beam to maintain the time synchronization, okay, if blockage happens. And the reflected beam can be used to maintain control plane information, such as time synchronization. And once that disappears, then you quickly get back immediately to the line of sight communication. Okay, so this is BeamSurfer, which is it is a quick mobility adaptation. It's a minimalistic protocol. It doesn't require any additional sensors or anything. Extremely low complexity, and we've implemented it in our 60 gigahertz millimeter wave test bed, and it's also blockage ready for indoor environments. So I'm going to show indoor, and I'll talk separately about outdoor. And it keeps a backup non-line of sight beam, which means reflected beam in memory, and it switches to that whenever needed. And here is the state transition diagram for the protocol. So for example, this is normal operation, and if and then if you see a change, then you do some receive beam adaptation, etc. And under certain conditions, you go to non-line of sight, etc., etc. Okay. Okay, experimental validation. So this is what happens in the translational motion. So what's happening here is that receive beam adaptation is going on here, but at certain points, and so you do a couple of receive beam adaptations, but then after that, receive beam is not enough. So then you have to do a transmit beam adaptation, then again receive beam adaptation, etc. Okay, rotational motion again, you see the same thing. And this is blockage recovery. So there's a blockage, and very quickly you come back to the non-line of sight beam and so on. All right. What about outdoors? The thing is, there are no, it is commonly, it was always felt that there are no reflected beams outdoors, not like an indoor environment. So people actually suggested a dense deployment of base stations, okay? And using maybe something like coordinated multi-point transmission or handover, okay? So, and but that is a very, very expensive solution. In fact, calculations suggest that you need something like 200 base stations per square kilometer to avoid outage. Okay, that's ridiculous. Okay, it's not going to work. So, do we need that? And no. So what their suggestion is, here's your base station. Here, I hate this animation, but anyway, you have it. And so now you have all these other base stations, and they can do coordinated multi-point transmission or whatever. Okay, and now what we have done is, experimentally, we have confirmed that there's always one reflected beam available from the ground. There's always one. Okay, so you don't need all this stuff. Okay, so this is Santosh, by the way, and this is his transmitter receiver setup. He's blocking it, and he's going to check that there is a reflected beam. Oops, sorry. Reflected beam of the ground here. Okay, so in the direct line of sight, this is the path loss, okay, when everything is fine. When things get blocked, like a pedestrian occlusion or something, you go down to minus 71 dBm. But this reflected beam off the ground allows you to maintain a control channel, minus 57 dBm. Okay, so this ground reflections, Santosh did a lot of testing, and he saw that on hard surfaces, like concrete, gravel, tar, like many of our built environments, there is always reflected beam, but not on things like grass. Okay, not on grass. And this is the type of path loss that you see in these outdoor environments. Okay? And so this is the basis of Terra, blockage resilient when outdoors. So we use a reflected beam off the ground, and it preserves connectivity during transient blockage and prepares the mobile for. Now, if it's a permanent blockage, then you have to do handover, and there's also a handover protocol he's developed, which is different from omnidirectional, because to do handover, both of you need to coordinate, which is very different from omnidirectional, and it doesn't require any additional infrastructure. Okay, and this is so ground reflection can support control plane traffic. We also found that the slight tilt of the base station may help towards the ground just a little bit. And you completely avoid need for dense deployments, prevents outage, preserves timing, and so on. And this is the actual experiments. Amazingly, he did all these things alone. Okay, which I find quite amazing. So here, this left side is what happens if you don't use a reflected beam. You have a catastrophic loss of signal strength. And on the right side here, oops, on the right side here, this work. On the right side, let's see. I never know how these things work. Right. Okay. So here is with the reflection, so it's not as catastrophic as here. Okay, and this also goes with a state machine, etc. And that's about it. Yeah. Thank you.
So thanks for the talk. So you mentioned as one of the early examples, someone just turning around, which is probably not an uncommon situation. So does that require then a completely different solution?
No, that's transient outage again.
But if you just turn around and don't come back.
Yeah, then if you don't come back, then it's permanent. But if you're just walking like this, then
right. So I guess my question was more, does then using this scheme lengthen the time that it's going to take to figure out that you need to switch to something else because it's it's a handover, right? So is there a cost to using that particular scheme in those scenarios?
It'll save a lot of outages, like for example, pedestrian blockage.
Right. For those,
it's right. Those things. It'll save as much as it can. And in the cases where it's irretrievable and you have to do handover, you're only delayed by maybe 50 seconds or thereabouts. Yeah.
Yes, I was wondering, you may have, I mean, if the motion is very fast, assume you have a car and something like that, whether there would be, because there is as mentioned, there is an overhead as soon as you cross the boundary between two beams, right? Whether would be some sort of adaptation to speed of the beam width, which would maximize spectral efficiency, taking this overhead into account?
Yeah. So for example, we structured it for pedestrian walking station. But you can also imagine cars, say 100, 200 meters away, and look at the angular motion and then design the beams and so on. Yes, it's possible.
And in that case, I mean, I was wondering, because you might have fading also, that here you have a dominant path, which is the reflected path on the ground.
Yes.
But there could be fading phenomena with several paths actually combined.
For the line of sight, you mean?
Yeah.
It's possible. Yeah.
Right. And so then how would you account for fading in the...
I mean, so you'll have to provision the transmit signal strength, etc., to work for you.
Oh, okay.
I mean, if the strongest beam you have is the line of sight beam, and if even that is not enough, then it's not supportable. But you can always manage the signal strength, provided it's feasible. You'll have to engineer it properly. Yeah.
Thank you.
How complex the algorithm is to be implemented?
I'm sorry?
About the complexity of implementation.
Very simple.
Really?
I mean, Santosh did it all by himself. Yeah. Just by himself. Even the experiment.
The alignment is also simple.
Yeah, very simple. Yeah. So we used NI software-defined radio operating at 60 gigahertz. That's it. So actually, one of my points is this is not something to defeat corporations. So we can actually use the millimeter wave band and all these. We don't have to do all these outrageous solutions. Very simple and things are possible.
It's extremely interesting because one of the key issues with millimeter wave is that usually you consume a lot of resources in the control plane in order to do the alignments and things of that sort. So if you manage to do it without almost any cost, it's major. It's enabling the deployment somehow.